Welcome to the Deep Dive. Today, we're putting away the neat, tidy world of static physics.
We are. We're diving headfirst into the messy reality of non-equilibrium states.
And our map for this journey is Chapter 43, Diffusion, from Richard Feynman's Lectures on Physics.
That's right. So much physics focuses on thermal equilibrium, that steady state where, averages don't change, everything's relaxed.
Right. But the real world isn't usually like that, is it?
Not at all. It's constantly changing, flowing, mixing. So our mission today is to figure out what happens when gases are not in that nice, neat balance.
And we're going to try and extract some key features, predict things.
Exactly. We'll look at processes like flow, spreading, even electrical current, and we'll do it using Feynman's style, simple, intuitive arguments based on molecular collisions.
Okay, let's unpack this then. We're starting from the ground up, with just a single molecule hitting another one.
That's the plan. Build an entire framework for these big transport processes, all starting from that one basic event, the collision. We need that microscopic rhythm first.
Got it. So let's kick things off. Picture a gas, but it's not in equilibrium. Maybe we have an ion in there.
Right, an ion, a charged particle floating in a gas of neutral molecules. And then maybe we switch on an electric field.
So the ion feels a force. It starts to accelerate.
It does, but it's not alone, is it? It's swimming in this sea of other molecules.
Yeah, so it's going to crash.
Inevitably. It accelerates, gains some speed, and then bam, it collides with a neutral molecule.
And what happens then? Does it just bounce off?
Well, the key simplifying idea here is that in the collision, it basically loses all the momentum it just gained from the field. It gets, randomized, a fresh start velocity-wise.
Okay, so it accelerates, hits something, loses speed, and then the field makes it accelerate again.
Precisely. That cycle, accelerate, collide, reset, repeat, that defines its overall net movement. We call that its drift.
And how fast it drifts must depend entirely on how often those collisions happen.
Exactly. Which brings us to our first really crucial variable, the collision rate. Or maybe, more usefully, its inverse, the average time between collisions. We call it tau.
Oh, okay. Like a tiny little clock for each molecule?
Sort of, yeah. If you watched one molecule for a total time, $2, and it had number one collisions in that time, well, tau is just dollars divided by dollars, the average gap between hits.
Okay, that seems straightforward. But what can we do with this tau?
Well, this is where it gets interesting. Knowing tau lets us talk about probability. You, the listener, might wonder, what's the chance a molecule flies for, say, 1 second without hitting anything?
Or even a tiny fraction of a second.
Right. And that probability, let's call it PT, it isn't just like decreasing steadily. It follows an exponential decay.
Okay, PT, I remember seeing that.
Exactly. So when time to do is 0, the probability is $1. It definitely hasn't hit anything yet.
Makes sense.
But as time goes on, the chance of not having hit anything drops off really fast, exponentially fast. It shows that long, uninterrupted flights are, well, pretty rare in a typical gas. Those little molecular clocks are always ticking towards the next collision.
Okay, so we have a handle on the time between collisions. But molecules move, right? They cover distance.
Yep.
How does time translate to distance here?
Good point. We need to shift focus from the time gap to the distance covered in that time. That's the mean free path, which we call the dollar.
Mean free path, the average distance between hits.
Yep. And the simplest way to think about it is distance equals speed times time. So roughly, the mean free path, dollars, is the average speed of Ziller times that average time to dollars. So the Billers have it.
Okay, the love is, yeah, that seems simple enough.
Yeah.
But what determines if Viller's big or small?
Yeah.
Like, what makes the path long or short?
Right. Is it like flying through nearly empty space or trying to push through a dense crowd? That depends on two main things.
Which are?
First, how crowded is it? That's the number density of the molecules. Let's call it number dollars. More molecules means more obstacles.
Okay, density. And second?
Second, how big are the obstacles? This is where we need Feynman's concept of the collision cross-section, sigma.
Sigma. That sounds geometric. Like an area.
It is. Think of it like this. Don't picture molecules as tiny points. Give them a sort of effective size. For a collision to happen, the center of one molecule has to pass within a certain distance of the center of another.
So sigma is like the target area. If the incoming molecule center hits that imaginary target disk around the other molecule, they collide.
That's a great way to visualize it. It's the effective area that triggers a collision. It captures the molecule size, essentially.
So if the molecules are bigger, sigma is bigger. And if the gas is denser, $10 is bigger. Both should mean more collisions, right?
Exactly. More collisions means the average distance between them gets shorter.
So the mean free path, $10, should get smaller if sigma or $10 get bigger.
Precisely. The relationship is inverse. Dollars is proportional to $1 figma dollar. Double the density, you have the mean free path. Double the cross-sectional area, you also have the mean free path.
Wow. Okay, that connects the microscopic size and crowding dollars directly to this average travel distance, level hours. That's neat.
It's a really clean result. It tells you exactly why dense gases or gases with large molecules have very short mean free paths.
Right. So we've got our basic tools,
Yes.
the average time taus and the average distance dollars. Now let's use them. Back to our special molecule, the S molecule, being pushed by some external force, $5.
Okay. And remember that crucial simplification we talked about.
The fresh start idea, that after each collision, the molecule completely forgets its previous velocity from the force.
That's the one. We assume the collision totally randomizes its direction and speed, wiping the slate clean before the force starts acting on it again.
Now, hang on. That still feels like a really big assumption. Does that, actually work? Doesn't ignoring a memory mess things up?
It's a fair question. It is definitely a simplification. Real collisions are messy. Momentum transfer isn't always total.
So why make it?
Because, as Feynman shows, even this simplified model gets the essential physics right for the average drift motion. We're not tracking one specific molecule perfectly. We're looking for the overall long-term effect of the force on many molecules over many collisions. For that average behavior, the memory erasure model works surprisingly well. It gives us the right form for the answer.
Okay, I'll trust the process for now.
Yeah.
So with that assumption, the force Vol acts on our molecule, mass dollars, for that average time tau between collisions.
Right. It accelerates it for time tau. So the velocity it picks up due to the force is acceleration, 1,000, a land dollars times time.
And that average velocity gained over that time is what we're calling the drift speed, right?
Exactly. Vogdiller is proportional to the force dollars, proportional to the time tau, and inversely proportional to the mass dollars.
Okay. Va drift proportional to the versed.
And this proportionality is so fundamental, we give the constant factor its own name, mobility, usually written as mu.
Mobility. So Va drift dollar fell.
Precisely. And comparing that with vol drift being related to tom, we see that mobility volt itself must be related to tom.
I see. Believe you, Tom, mobility depends directly on collision time and inversely on mass.
Makes sense, doesn't it? If collisions are rare, large tau, the force acts longer, more speed builds up, higher mobility. If the molecule is heavy, large dollar is harder to accelerate, lower mobility.
Okay, that clicks. And you mentioned an application,
Right.
like electricity in gases.
Yes, ionic conductivity.
Yeah.
If our S molecule is an ion with charged dollars and it's in an electric field, a dollar, then the force dollars is just 2 times.
U pop, simple enough.
So the drift speed is vol drift, mu F mu Te. The ions drift because of the field.
And drifting charges make an electric current, right?
Exactly. If you calculate the total current dollar flowing across, say, a container of this ionized gas, it depends on how many ions there are, their density, the charged dollars, and how fast they're drifting.
Let me guess. We can
Wow.
put it all together.
You find the total current dollar is directly proportional to the applied electric field of dollars, which is essentially Ohm's law, current proportional to voltage, since field is related to voltage.
Wow. So Ohm's law just pops out from thinking about ions bumping into neutral molecules.
Basically, yes. Derived from first principles using just collisions, average time, and mobility, it's a fantastic example of the power of this kinetic theory approach.
Okay, that's pretty cool. We pushed molecules with a force and got Ohm's law. But what about movement without an external push? Like if stuff just spreads out on its own?
Now we're moving to the second major topic, molecular diffusion. This is about spreading driven purely by differences in concentration or density. No external force needed, just random thermal motion doing its thing.
Right, like if you open a bottle of perfume in a corner, eventually you smell it across the room. That's diffusion.
That's exactly it. The perfume molecules spread out from where they're concentrated to where they're not.
Why does that happen? Just randomness.
It comes down to the density gradient. Imagine you have more perfume molecules on the left than on the right, and picture an imaginary boundary line in the middle.
Okay.
Just by random motion, molecules are crossing that line in both directions. But because there are more molecules on the left, statistically, more will happen to cross from left to right than from right to left in any given time interval.
So even though movement is random, the density difference creates a net flow away from the high-density region.
Precisely. There's a net flux, or current, of molecules purely because of the non-uniform density, the gradient detics.
So we could define a diffusion current. Let's call it the net number crossing a unit area per unit time.
We can. And the physical law governing this, often called Fick's first law, states that this diffusion current jjs is proportional to the negative of the density gradient.
Negative because the flow is down the gradient from high to low density.
Exactly. Jjs equals NLD, GNDF.
Okay, and that dollar must be...
That's the diffusion coefficient, dollars. It's a constant that tells you how quickly the diffusion happens. High dollar means fast spreading.
Got it. So we have mobility for force-driven drift and diffusion coefficient dollars for density-driven spreading. Are they related?
Ah, now you've hit the absolute highlight, the real synthesis of this whole chapter. Yes, they are profoundly related. This is where we get the Einstein relation.
The Einstein relation. Okay, this sounds important.
It is. It connects the response to an external force, mobility, with the response to a density gradient, diffusion coefficient. The link is temperature. $2.
Don't keep us in suspense. What is it?
The relation is $0 is mu k te p dal, where future is the Boltzmann constant.
U dollar, a p te, okay. Let that sink in. Diffusion and mobility linked by temperature.
It's beautiful, isn't it? It tells us that the microscopic jiggling and randomness caused by thermal energy is precisely what governs both how easily a particle diffuses and how readily it responds to an external force. They seem like different processes, but they stem from the same underlying molecular motion.
So higher temperature means more vigorous random motion.
Which leads to faster diffusion, larger away, and makes the particle respond more effectively to a force, in a sense, related to the Feynman. It's a unified picture.
Incredible. Okay, one last piece you mentioned. Thermal conductivity.
Right, the final application in the chapter. Heat flow. This is transport driven by a temperature gradient, hot region next to a cold region.
So, similar idea to diffusion, but instead of molecules spreading, it's energy.
Exactly that. Hot molecules have more kinetic energy. They randomly move, colliding with colder, lower energy molecules. On average, more high-energy molecules wander into the cold region than low-energy molecules wander into the hot region.
So energy gets transferred from hot to cold via these random collisions.
Precisely. It's diffusion, but the quantity being transported is thermal energy.
And there's a constant for this too, thermal conductivity, kappa.
Yes. It relates the rate of heat flow per unit area to the temperature gradient. dqa dtt in SAPA a dt dbx dollar. Again, the minus sign because heat flows from hot to cold down the temperature gradient.
Okay, and I assume kappa also depends on those same basic collision properties.
It does. When you work through the details, you find that thermal conductivity, just like mobility and diffusion, ultimately depends on things like the mean free path dollar and the average molecular speed, which itself relates back to tau.
So all these different transport phenomena, drift under force, diffusion under density gradients, heat flow under temperature gradients, they all boil down to the same basic picture of molecules moving, colliding, and carrying stuff.
That's the core message. Kinetic theory provides this unifying framework. It all comes back to the collision time tower and the mean free path dollars.
Right. So let's recap. We started with just the idea of molecules colliding. That gave us the tau, the time between hits, and the dollars, distance between them.
From tau and the molecule's mass, we got mobility and Neuer, describing how it responds to a force, leading to drift and electrical conductivity.
Then, from random motion and density gradients, we got the diffusion coefficient dollar.
And the absolute stunner, the Einstein relation, d a dollar equals mu log p2o2, linking those two seemingly separate processes through temperature.
And finally, thermal conductivity kappa, showing energy transport follows the same basic rules.
It's a beautiful demonstration of how simple microscopic models can explain complex macroscopic phenomena. The unity revealed by DLLP-K2O is really the key insight. The response to force and the response to gradients are two sides of the same coin, minted by thermal energy.
So, for you, the listener, maybe the thing to ponder is this. Feynman used some pretty rough approximations here, didn't he? Especially that fresh start collision model, wiping out all memory. How surprising is it really that such simplified pictures manage to capture the essence of these processes so accurately and give us laws like Ohm's law and the Einstein relation? Maybe nature is simpler at its core than we sometimes think.